Hello everyone. In this experiment, we'll be looking at how to interface and control a stepper motor using a microprocessor kit and a stepper motor controller module. So now let's look at the aim of the experiment. In the experiment, we have used a microprocessor kit, which is the ET-8085AD LCD, which was manufactured by Excel Technologies. The aim of the experiment is to interface a stepper motor with 8085 using 8255, which is a programmable peripheral interface. The experiment will help us understand how a microprocessor can control precise mechanical motion using software instructions. In the system, we have hardware components like the 8085 processor and a programmable peripheral interface, a driver circuit, and finally we have a stepper motor. Of course, the objective is not just to rotate the motor, of course. It is to understand how the instructions we give to the microprocessor can be translated into mechanical movements. So in some notion, you can think of it as a hardware software integration in embedded systems. The second objective is to study how the speed and direction of rotation can be controlled through software. This is very helpful because let's say in robots, the robot may have to move its hand slightly or tilt its hand. So at such times, we have to exactly be able to translate the software into mechanical movements. So this can act as a foundation for that. The third objective is to understand how the step angle, pulse counting, and the sequence logic work in the system. From a microprocessor's point of view, this experiment will help us understand how machine instructions can control electromechanical devices, which is very necessary for understanding a lot of things. So now we'll be looking at the devices that was used in the experiment. The first is the microprocessor kit. As I told you, in this we have used ET-8085 LCD kit. The image was taken in Microprocessors Lab from the physics department of IIT Roorkee. And this is the stepper motor controller interface. It's ET-SMC, which is the short form for stepper motor controller. Also, we have used a FRC cable, as you can see here. The FRC cable here is connected to the J1 pin of the microprocessor kit. I'll be explaining what the J1 pin and the 8255I pins mean. And then of course we have also used a stepper motor. So now we'll be looking at what a stepper motor means. I hope all of you have an idea of what a DC motor is. A stepper motor is a brushless DC motor. In a DC motor, the movement is continuous, meaning it's not discretized by anything. You can see the DC motor video for this. I have attached an animation of how a DC motor works. In a stepper motor, the motion cannot be continuous. It rotates in discrete steps. Every electrical pulse that's applied to the motor results in a fixed angular displacement. Usually, stepper motors have a step angle of 0.9 or 1.8 degrees. In our experiment, we have used a stepper motor that has a step angle of 1.8 degrees. So naturally, the number of steps that have to happen for one full revolution is 200, which can be calculated from the simple formula. And what this means is, if in for one step 1 by 200 revolutions are completed. So for one pulse, 1 by 200 revolutions are completed. So for one complete revolution, you need 200 pulses. This makes stepper motors useful in applications which require precise positioning, such as computer neural control machines, and as I mentioned, in robotics as well. So now we'll be looking at the working of a stepper motor. This is just an animation which I got from Wikipedia. You can see here the stepper motor slightly moves. The rotor slightly moves depending on the magnetic field applied to the stator coil windings. So for one pulse, the rotor rotates by some fixed angular step. You can see that, I believe, here. The rotor rotates in discrete steps. Yeah, the stator consists of many electromagnetic coils, and the magnetic field generated in this electromagnetic coil is can be determined using Ampere's law. The rotor is a permanent magnet, and it aligns itself with the magnetic field produced by the stator. This creates a stable equilibrium position. When the next coil is energized, then the magnetic field will be shifted. For example, when the first coil and the third coil are energized, you have a specific movement, and when you switch the coils that are being energized, the magnetic field shifts, which leads to alignment of the rotor according to the magnetic field, which leads to a small rotation, and then you can continuously vary it in steps like this so as to produce a complete rotation. The amount of shift depends on the motor's internal pole structure. That is, you see, the rotor that we have does not have a single north and south pole. It has many north and south poles. So, and according to the position of the north and south poles, the shift will be determined. Now we'll be looking at the working of stepper motor in detail. So the motor operates using two main phases, which are say phase A and phase B. When the current flows through phase A magnetic field is generated in a specific direction, which we can determine using Ampere's law. And subsequently for phase B, the magnetic field is in a different orientation. The rotor tries to align with this rotating magnetic field, and the digital switching patterns, which actually cause the phase to change, lead to the mechanical rotation. That's exactly why the digital logic can control physical movement. More clearly, we use something known as a for the switching action here. We don't no specific hardware is required. We can change the current that is passed through the coils using digital logic. That's how we can change the direction just by changing the instructions given to the kit. We'll be looking at how we can do that shortly. So now we'll be looking at the stepping sequence. Say we energize the phase A coil first. Then the rotor aligns with the phase magnetic field of the phase A. And then we energize both phase A and phase B. Then the magnetic field would shift slightly. Then let's say only phase B is energized. Then the magnetic field would be shift again. And this would create discrete steps, just like how we saw here. You can see here. Yeah, this would result in discrete steps, and then finally it would lead to a complete revolution. To just reverse the direction as I explained here, you just have to explain the instructions given to the software. This is the most important section of the experiment, which is interfacing with 8085. All we saw till now was just theory. The stepper motor actually cannot be connected to the 8085 microprocessor. You may think why. Because the microprocessor can only supply a few milliamperes of current, maybe 1 milliampere to 5 milliampere. The motor requires much higher current, which means we have to use a programmable peripheral interface now, which is the role of the 8255, as I explained earlier. 8255 provides 24 input-output lines, and the microprocessor writes out a digital pattern to a port using the out instruction. We'll be looking at the working of the code again shortly. Then the driver circuit energizes the motor windings. The control chain is we have an instruction, it reaches the port output, then it reaches the driver circuit, then the coil current, and then the magnetic field is generated. Then we get the mechanical rotation. This is just something that I already explained. For example, if I write MVIA05H and out00H, the processor sends a binary to this port, which is the accumulator receives this, and out actually means the accumulator, the data contents of the accumulator get displayed in this port address. So the microprocessor sends the binary to that port. These pins are connected to the driver circuit, and each of this binary data means something to the driver circuit. Then the driver circuit amplifies the current. This is the flow diagram of the entire experiment. We initialize the 8255 first. Then a stepping pattern is loaded into the accumulator. Then we introduce a delay. Then the next pattern is loaded and the process continues repeatedly, resulting in a mechanical rotation. So this is one of the most interesting sections of the experiment. I'll be explaining you about the code now. MVI-A80. This initializes the 8255 in mode 0 and configures the port as an output, this specific line. This is the opcode which was used, and this is the mnemonics. This is the register in which the opcode is typed. So this is the step 0. FA in binary is basically 1111 1010. So the 4 lower bits are 1010. These 4 lower bits are responsible for coil excitation, and they give a specific combination of windings. Calling 2030 creates a delay, and then now we change the binary pattern, and the rotor moves and the magnetic field shifts. Again we change the binary pattern, the rotor moves and the magnetic field shifts, and it happens again, and this is the final shift in the cycle, and the sequence repeats itself because we have used a jump code here. This is the basic explanation of the code that was used for the experiment. So in the experiment, some difficulties were actually faced. Thing is, we have to troubleshoot what is actually happening in the circuit if something is not working properly, because the problem could be anywhere in the FRC cables, in the kit, in the interfacing module, or the stepper motor itself, or the connecting wires, or the power supply. It can be anything. So to properly troubleshoot the experiment, every single component has to be changed every time. Yeah, that's how you do it. Also, while the motor is rotating, it should not be touched because it might injure you or it might damage the stepper motor. Also, the motor may not rotate sometimes due to insufficient torque. So a small push would be helpful to rotate the motor. In the next slide, we'll be looking at the videos which were taken in the lab during the experiment. So you can see the slow motion video. You can see the stepper motor rotating to and fro. This was actually written in the code, and the code was modified a little bit to produce this kind of motion. This was also one more video which was done using the same code. You can see that the stepper motor is rotating. So yeah, that's it. All of the images were taken in the microprocess lab of the physics department in IIT Roorkee, and the other images were properly licensed under Creative Commons. The source was Wikipedia. Thank you.